Now, let me put, in order to get that answer, I'll try to get the answer, otherwise I'll answer this. I think they have gotten very good, this is a good thing what you guys are doing, playing with it and So, first question, basic question is, I know this also very important why Professor Berra were looking at this kind of topic. Why do we care about in controller design using reinforcement learning or any machine learning method? What is the benefit? We don't do anything unless there is a benefit, right? There should be some benefit. So there are so many different methods in control design, right? There is the PI, PID, there is also standard optimal control that we saw where you need the dynamics, right? We are comparing always. There is also robust control method. There are so many different sliding mode. There are so many different methods which are nonlinear. Okay, so in general, all these control methods can be classified into linear method, k times x, right? That's linear, and there is nonlinear. Understood? So, like the neural network-based method is nonlinear. You have seen that, all that stuff, right? And we also saw for linear systems, we had the optimal control k times x. That Kalman gain is a linear gain, k times x, right? But the way you obtain the gain, you have to solve all those Riccati equation and all that. That process is nonlinear, but at least once you get the gain, U is basically linear with respect to state, okay? So my question is, let's take a recap. What are the benefits? I know you guys have done so many lectures now with me. What do you think, what is the major benefit of using the reinforcement learning that we are doing? Both for linear system, we did for linear system, plain linear systems without network. We just extended that to the network control system. Remember that? I showed you how that changes the A and B matrix, right? The same thing we did even for nonlinear system. We had so many examples in nonlinear, a robot manipulator, some other nonlinear systems. So, and the same thing, plain nonlinear systems, we also had the network in there, and we also got something FGK, HGK, whatever, with some packet losses. And we understood the reason it changes is because you are bringing in a network and becomes stochastic. All that is fine, but why we use reinforcement learning? And what is the one major advantage you have seen using reinforcement learning? I think they did a good job. I think it looks like they're doing very good. They have been playing with the code, they're exploring. Basically, that's what I say. You remember we talked about exploration and exploitation. So they are exploring and they're finding, and those are positive. You will see that. So what is the good thing about reinforcement learning? Why do we have to study, and why this would be a future? At least even in the control design. And don't feel shy. Go ahead. Right, universal controller. I think that's the major advantage. So basically what you are saying is, even if I don't change the dimension of the system, I change the A and D matrix if it's a linear system, that controller should work. The same thing applies to nonlinear. Instead of two-link robot, if I pick a F and G, some other nonlinear, it should work. Because one of the things you are doing there is your learning the system dynamics. So that means it's like a plug and play. I change the system, maybe a batch reactor, you got A and B, but tomorrow let's say you're working on some other system and you have a different A and B, and you can still use the same controller. And without any changes, whether linear or non-linear. Maybe the only change you may need is fine-tuning those learning rates or something. Okay? It does work for both stable and unstable open loop systems, right? Batch reactor is a open loop, inherently open loop, unstable systems. So it's more like a universal controller. Now, they also found exploration, it also works like this. So let's say you have 4 states. Okay? You expand, and let's say that 2 states are dependent on the other 2. it still works. Because what is important, that's what they were asking, what is important is when you are trying to approximate either the Q function or you are using neural network to approximate, as everything is an approximation. So if you don't feed some input, you may end up in having some error. Many times if that error is not significant, you still have a reasonable good performance. So but there may be times where if you remove that state out, suppose one of the states are very important, everything depends on that. But if that state is not fed as an input, then you may see some significant degradation. One of the benefits with neural network is, essentially they claim that neural networks have graceful degradation. Even if you chop off some neurons, it should still produce a reasonable output. So this is one reason, even if you are not feeding all the states. But it may not be always true, because in some cases, you may have to feed all the states, like independent states, Yeah. Okay. So what they are saying is, I'm very happy they are trying to change the dimensions. They are changing the inputs to the Q function or the neural network and see whether it still works. So it does work, because as long as it's able to reconstruct the dynamics, it should be able to. And everything is an approximation. If there's only a small change, you don't see a big error in your outcome. You know what I mean? So this is why people are after. And in the good thing with our approach, remember I mentioned, compared to the CS people, computer sciences, we do in real time, because in control is a real-time system. We don't really do offline, and so it's not like a path planning. In path planning, you can do that. But for real-time control, we have to do it in real time. So that's another important thing, and it has to be running in real time, okay? So keep this in mind. That is, even if you remember anything or not, this has to be something you need to remember, that this controller is more or less universal. And that's what I showed you when I was showing the engine stuff. Remember, I ran on 2 different engines, and that's practical. It does work without any major issues. You see? So that is benefit compared to a lot of different methods. A lot of different controller methods are specific to the system that you consider. If you change the system, you have to redesign everything. You see? Here you don't have to redesign. The only time where you have to redesign is if the structure of the system is different. Let's say AX plus BU, you have a completely different system, AX or AX something. For nonlinear is easy, f of x plus g of x times u, f1 plus g1 times x2, f2 plus g2 times u. There are different class of systems. Then you have to come up with a different design. Otherwise, just changing the dynamics, you don't need to change the controller design. Okay? All right, so any other questions? Any other questions? So anybody explored? I think the ones in the front, they were really, those are nice things that they're observing. I want you to run the intro code or any of them. Unless you run and understand, you probably won't have that real depth information or knowledge. And remember, they are faculty, and they are also have other commitments like teaching classes and so forth. So they're still able to spend some time running these MATLAB code. So I think I encourage others who are MTech students to do the same, And we only have a couple more days. Tomorrow and Thursday is an exam. Today and tomorrow, that's it. Yeah. So what other questions? For the scheduling, because that's we call cross layer. The 8.3. Let me see. Yeah, this is the scheduling algorithm. See, this is the scheduling algorithm. You see that? And this is basically trying to access the network and applying. So this is the optimization algorithm. So 8.1 is just the optimal control, trying to come up with that the optimal control policy. Then what you do, 8.2, you basically looks at how you implement the controller. So 8.2 if you look at 8.2 what it does is, okay, you have so many pairs with states, you're looking at a sampling interval, KTS and K plus 1 TS. You receive and implement the control inputs from the controller. If multiple control inputs have been received, then apply the most recent one, you see? Okay, and discard the other ones. Else old control input arrived after new control input being received, then discard the old one and apply the new one. So this is just the logic, just a zeroed out logic. This has nothing, whereas this one, this 8.1, is trying to determine the gains, right? The gains, and also the step number 7, if you look at it, you are trying to determine the optimal control input, which is U hat. Okay? Now what is 8.3? So 8.3 is a scheduling scheme. Okay? So in 8.3, basically what you are saying is, you have a parameter which is B naught. This is a weighting parameter. And here is your cost function. So it's 2 to the power of Ri plus, see, the Ri is the traffic. The traffic that that particular system has to transmit. Okay? And you see that there's another term which is the delta. This is the cost from the controller. So you are combining this and then you are trying to maximize that as a utility function. Okay? So now remember, it's a distributed. That means not every subsystem will communicate to other subsystems. So it uses only local information. Remember. So if you have to know what others, how much data others have to communicate, then does it become distributed or centralized? Does it become distributed or centralized? Let's say there are 4 people, imagine, and all 4 people want to do something. And I am a person that is trying to decide who comes first. If all 4 communicate to all the others, would that become distributed, or they decide, or I decide which one goes first? Which is what is meaning of distributed. You remember that here? The word distributed scheduling. What is the meaning of distributed? There is no communication between each subsystem. Now what is the reason? Because if you have to communicate, that would cause overhead. And that can cause problems in the network. If everybody, so to avoid this, we basically don't use the communication of how much data that each subsystem has to communicate. Instead, basically each subsystem would try to maximize this utility function, and that information is used as part of what they call back-off interval. You see that equation there? This back-off interval uses the traffic that each subsystem has to transmit and also the cost function. So only one would have the highest value, or it should have the shortest back-off interval. And that is the one that is basically given to go, the green signal to say that, okay, go ahead and transmit. Once you do the transmission, then again you start again, and then you look at which other subsystem has the smallest back-off interval. Each of the subsystems would do on their own. So they don't communicate. By doing that, they are avoiding this extra overhead. So there is nobody kind of scheduling, trying to say, okay, how much data you have, how much data you have. So nobody is trying to do that. It automatically is done by using this back-off interval. So each subsystem, based on that, their own utility function would decide how long to back off. You see? So that's what is given here. So that is a function of 2 to the power of the traffic plus the cost that each subsystem is trying to minimize. So this utility function is going to be maximized. Because of maximization, this value bi is basically, if you look at it, this is averaged. This value will be smallest for the one that would require the media to transmit first. So this algorithm is mainly for scheduling method. Okay? And then you basically get the access to the wireless network. Then you find the smallest one transmits. If the transmission is over, then you update the schedules by selecting that beta. So if the beta value is higher, it gives higher priority. So the beta is multiplied by the amount of traffic that it has to transmit. So algorithm 8.3 is mainly for scheduling. 8.1 and 8.2 is mainly the optimization of the control input and how it operates, that's what is 8.1 and 8.2. Okay? Yeah. This is in the link layer. The link application layer, only the control and all other applications, right? So this is a part of the network. So the network has so many stack, right? Remember, so if you look at the network stack, so you see that here, so the physical, here is the physical layer. Physical layer is the physical wire. So the physical is the physical wire. So like, you have a little thing that transmits. So in this case, that Ethernet cable, for example. But then you have the link layer. Link layer basically does the scheduling. Multiple, because the wireless, there are multiple nodes are connected, who goes first. And there is a network layer, it basically does the IP addresses. It provides the IP addresses for multiple. Then you have the transport layer. Transport layer basically gives the connection at the end-to-end connection at the highest level. How to communicate from user A to destination D or something, And all our methods basically stays in the application layer. That is correct. Standard, that is correct. That is correct. Right. And only we need this link layer because we want to schedule based on how important which node has to transmit. Because only one can transmit, so we have to create priorities in a manner that they are not communicating. And we don't want a centralized scheduler. Remember, like in your core schedules, what do? You define a schedule and then you give it to the registrar. He is the centralized person. What does the registrar do? He runs the schedules, make sure there are no conflicts. So here there is no centralized scheduler. That comes below. That we are not dealing with TCP/IP for the control design. We are using the scheduling, only scheduling. The TCP/IP is the way to communicate. Once that scheduling method decides who goes first, then the TCP, then that node will transmit and it transmits through the TCP/IP. That's right. They are trying to transmit. Right, right. There they're distributed, so it decides who goes first. That's right. That is a part of the network. That is correct. That is, it is a dedicated hardware. It's a hardware which have different layers in there. Yeah, it's more modular. It's not like physical hardware. There's one piece of hardware, but within the hardware they have different. In the software level, they have different call layers or it's written module. Each module does a specific function. Well, no, in control also you may have. Like a good example in a control is you have a low level controller and then you have a high level, right? Like in a feedback linearization, you have two loops. The inner loop is basically canceling the dynamics, and the outer loop is basically a linear controller. It's very similar. It's a part of the same controller, but you have two loops, the same thing here. So we are not changing the transportation layer, we are not changing the network layer, we're only changing the link layer which does the scheduling. And that makes a big difference, because if there are two people and ready to transmit, one is given the priority, the other one has to wait. So there is an issue, right? If he waits for a long time, you are running it in open loop. You see? Exactly. Okay, any other questions? So today we will add event triggering. You will see that. That's another way. Here, there is no event triggering. Every system is ready to transmit, right? So they always have data. Because you are not using a switch to decide whether to transmit or not. Whereas, when we decide that event triggering, there is another control mechanism where you decide whether to transmit or not. Yeah. Okay, any other questions? So, based on what you told me, you're able to run the programs, right? At least the intro to RL and everything. You change even though the dimensions are different, and in your case, you didn't change the states. Yeah, you're normally supposed to feed 4 input if you are changing it to 4. But what you are saying is you didn't change it, it did work, right? And primarily because in those instances, maybe the system is able to construct that dynamics using the 2 states. Yeah, because rate of change of position is velocity, rate of change of velocity is the axle. So sometimes when you have that kind of states, it should be able to construct. Yeah, but not always. You know, not always. So, any other questions? What else did you guys explore? Right. That's right. It doesn't. Yeah. I think that's the way to go, because remember, there's a lot of MATLAB code that we have given, right? For each chapter, there is, even though it's one example, this example has quite a bit of, so many cases, because like Professor Bera mentioned in that assignment, he kind of split them individually, like traditional controller, we have done the optimal controller. You know, there are different cases we are doing. Although the code might, combine it, but, so definitely there are multiple controllers you are comparing. So it would take you some time to digest how is it written, and the reinforcement learning controller is also involved, right? Remember, we have 2 neural networks if it's nonlinear, and so it is involved. So certainly it is going to take you some time to digest and try to understand the MATLAB code. So we don't expect that as he and I, because we had only like less than 2 weeks. Remember, Friday we have the assessment, so we started on Monday, so hardly we had 5 plus 4 days, 9 days, right? like you said, is the whole book. So it's basically like a crash course. And most of you don't have the background on different topics, right? So it's going to take you a little bit time. So we all understand that. Okay? Any other questions? Yeah? No. I think the basis function is the same. Remember we talked about in an easy understanding is if you have a 2 by 2 matrix, the rows or the columns have to span the direction in order to be linearly independent, right? So if you remember the unit vectors that we look at it, independent linearly. So if you have 3 by 3 matrix, it's 1 0 0 0 1 0 0 0 1. Those are the unit vectors we talk about that basically span. They are linearly independent. The same idea in that polynomial basis you see many cases. It has to, there is an equation that to get that basis function. And unless you do that, that network activation function don't form a basis. Now, why is that important in the neural network literature? If you are using a single layer neural network, that means one layer of weights you are adjusting, the activation function has to form a basis to the original nonlinear function that you are trying to approximate. You see? Now, if you go from a single layer to multiple layer, let's say 2 layer, you can relax the basis function. You don't need to select it because you're tuning the hidden layer weights, and that if you tune it properly, it automatically can form a basis. You see? So that basis is very important. This is a theoretical result that we cannot skip. Yeah. So, but you can pick, we are picking polynomial. If you remember that y square, y1, y2, if you have multiple. But you can pick like trigonometric functions or splines. So some basis functions are better than the other. Now, not theoretically it's not shown, but by ad hoc methods, like you use them and you compare. But nobody at this stage knows how to select a basis function for a given problem. Yeah. So somebody will become famous if somebody can find out that. Yeah. You see? They're using a polynomial, yeah, because it works. Polynomial, remember e to the power of x, you expand like a polynomial. Exactly. Yeah. Only thing is you truncate it. You don't take all infinite terms. You basically use a few terms which are mainly, based on the number of neurons. Based on the number of neurons, you see? That's the... Yeah, then you will have 15 inputs like so many different combinations. Exactly. That's right. So a good example is e to the power of x. I gave you that example. If you have more neurons, you are taking more terms in that expansion. So if you take more terms, it's more accurate. When I teach my 5000 level, which is basically senior neural network class, I show them like, e to the power of x, and I plot them like a linear term. And so I show them how it becomes more accurate as you increase the number of terms. Exponential. So you can plot it and see e to the power of x, and you keep adding it, and you can see what happens if it's 1 plus e to the power of 1 plus x minus x square over factorial 2. So as you keep adding it, you see that it gets more and more accurate to the e to the power of minus x. Yeah. So that's what is happening, and that constant terms are your weights, right? You're multiplying that to the basis, which is 1 plus x, x square over factorial 2 plus x cube over factorial 3. Yeah. What else? I know I don't hear anything from other students. There are many who come attending the class, but I don't hear anything. So I want to see at least 1 or 2 questions from the back. Otherwise, I assume you guys understood everything. It's only binary. You don't understand anything, or you're understanding 100% that you don't have any question. Yeah. Right? Right. Right? Same. Then it should work. Right. No, but that, right. So, no, it should work if you, as long as you have the states, okay? But remember, there is, theoretically, when you say the dynamics are same, I already explained earlier, we call that as a structure. Then, when you express a nonlinear system, there is a structure. Remember, I asked you a question also. What are the other class of nonlinear systems? Let's answer that question. Remember that? Did anybody found an answer for that? See, that's one of the questions I asked you. One of the ones that we are selecting is affine system. Remember, affine system is x dot equal to f of x plus g of x times u. That's called, in nonlinear control, a nonlinear system in affine form, because the control input appears like linear. G of x is more like a B matrix. Okay? Now, if that structure changes, then you have to redesign your controller. But let's say you take x dot equal to f of x plus g of x times u. Let's say f and g for a robot manipulator. You take another example. You have a different f and different g, but still in the affine form. You see what I'm trying to say? Then the controller should work. Well, in some of the controllers, you may need the precise dynamics. So, for example, I'll give you a robust control. Let's say, in a typical robust control, you have to know the bounds on those nonlinearities. So, if you are changing the system, the bounds can change. You see what I'm saying? So, in the robust control, you assume that the bounds are known. Okay, because you use that information as part of the controller. So this is one of the drawbacks with robust control is we all claim, because if you pick a larger the value of the bound, that means you are applying more control input than is needed. So let's say your maximum value of your dynamics, that's what I mean, is 10. In a previous case, you had 100. And you use the same bound, 100. What will happen? You are applying 100 to the system which maximum value is 10. So you're wasting all that energy. So robust control, you require the dynamics. Nonlinear control, you do require the dynamics, some part of the dynamics. You see? Yeah. That's right. And it has to be in that structure, like x dot equal to f of x plus g of x times u. So if you change that structure, x1 dot equal to, so what is the other form of nonlinear control, nonlinear systems other than affine system? Let's talk about it, because that's where it's going to make a difference. So you're assuming that it's going to be expressed in the same structure. It may not be. You see what I'm trying to say? A missile could be written some some other form, like somebody said non-affine. So non-affine is x dot is equal to some nonlinear function of x comma u. That structure is different from x dot equal to f of x plus g of x times u. You see what I'm saying? So that's the only case where it doesn't work. But if you have two systems, the same structure, and you have f and g are different, it should work. That's what they found out. Whereas if you take adaptive control, it uses some assumptions, and those assumptions may not be hold if you change the system. And robust control has a different set of assumptions. So only with machine learning, this approach that we are dealing with, as long as the structure of the system is the same, then the controller should work, provided maybe you need to adjust like the learning rate, you know what I mean? Because that specifically depends on the dynamics. Remember in the material we have some bounds, right? The learning rate has to be less than this. Yeah. So you may have to adjust my small things, but otherwise it should work. And that's what I showed you. I have picked two engines. I use the same controller. Each engine has different size, the actual cylinders inside them, you know. So that even though they are different, it should still work because it's just able to approximate it. Engine is an engine. Okay? Yeah. It should work. That's the beauty. Yeah. Doesn't matter. What is inside the F and G doesn't matter. What is inside F and G doesn't matter. It's the structure, it matters. The only changes you may have to make in some cases is, like what she said, you may have to feed more states, right? Depending on the number of states, right? You know? Yeah. The fundamental thing is, remember we talked in the first class, Lipschitz continuous. That is the main. So if you're picking a gas turbine or some other system, it has to be Lipschitz continuous. So there are some assumptions that, but it doesn't matter what is inside. You could actually have the code, you can change the system without changing the dimension. Yeah, I think they have already explored. You change the system dynamics, let's say inverted pendulum or something else, okay? And try it. It should work. Yeah. What else, guys? I know we are ready to take a break with tea. That's okay. We go back to the slide so that it is a little bit more room here. Okay. So let's say that you have x dot right? This is a nonlinear system. We call that a affine system, right? So how do you do the feedback linearization, guys? Without looking at the Lie algebra. I know some people said raise their hand, nonlinear. Did you guys do feedback linearization? Yes or no? Huh? So, yeah. How do you do that? So remember, the most simplest way is what? U equal to G inverse of x minus f of x plus v. This v is called auxiliary input, right? So if you plug this equation back here, what you get? So you're taking this is a outer, we call inner loop. So you're cancelling the nonlinearities and you're getting a linear system. And use here, you can use like minus k times x. If it's a regulation problem, then you can show that's a linear controller. So then you show x goes to 0 as t tends to infinity. Or if you want to do a tracking problem, this is regulation. If you do tracking, you do what? So you pick v, in this case v equal to minus kx, v equal to xd, right? So then what happens? X dot equal to xd minus ke, or e dot plus ke equal to 0. E goes to 0, right? As t tends to infinity. So this is a tracking problem. So now that's what I was trying to tell him. You see this? You need that G inverse. Now, if G is a vector, you can take the inverse. So, but then in the nonlinear control, you don't need the inverse. If you use the Lie algebra, Lie derivatives, then you can actually construct such that you can actually see that you don't need it, okay? But here you may need it if you are blindly applying this. This is feedback linearization. So this is what is called structure. Now, did you guys do this? Did you guys study in nonlinear control? Do you know what type of system is that? So I know there are some who raised their hand, they studied nonlinear control. Did you guys study that system that I wrote on the left? No? No, I'm not asking you to a specific example. I'm asking you what class of system is that? So the right hand side is affine form, right? Remember I said that. Nonlinear system in affine form. So what about the left? So Bhanu Pratap, you asked this question. If you're using a controller for the right hand side and you try to use it for the left, it doesn't work. You could still make it work by kind of fooling something, and we have done that. But you see that the structure of the control system from left to right is different. You see that? So in the left side, you have 4 nonlinear functions. What are the 4 nonlinear functions? F1, G1, F2, G2. On the right hand side, you only have F and G. Okay? So we call that as a different structure. You see? But whatever is inside, if you have that X, you should be able to reconstruct it. So what is that called? The left hand side, that class of system is called what? I asked you to check as part of my question. So there are some who did nonlinear control, right? I know somebody is looking at it, searching the Google. So the nonlinear control, which, did you guys use any book? Khalil? Oh, then you should know. If it's a Khalil, that's a good book. Yeah. That's a good book. So it starts with a lot of math, Lipschitz continuous and all that stuff, and then it gets into, linearization, right? It starts with that, and then it gets into all the way. So that class of system is called what? It's called strict feedback system. Have you heard of that, strict feedback? So this is affine system. The left hand side is called nonlinear system, nonlinear strict feedback system, or this is affine. So where is that strict feedback system? What is an application of strict feedback system? What is an application? Did you guys study the strict feedback? Any of the nonlinear, did you guys study the strict feedback in your nonlinear control? Did you guys study? No? Or maybe you don't remember. Okay, so remember when you incorporate actuator dynamics. So if you remember, you are flying a plane, the plane has two engines. Engines are the actuators for a plane, right? So the engines are huge and it has its own dynamics. Okay, it has its own dynamics. So if you look at the example of robot manipulator, we are not incorporating the dynamics of the actuators. It's only the dynamics of the arm. You see? So if you bring in the actuator dynamics, then it becomes a strict feedback form. So a lot of times actuators have to be considered as part of the control problem. And actuators also are huge, like in a plane, and they have their own dynamics. So usually there is the actuator dynamics, and then the bottom equation is the actual physical system. Okay? So there is a reason why we have that. As long as you do that, it takes care, no problem. Okay? Right. That's why I said you could write it, you could fool it. But not always it would work. Not always it would work. There are cases where it doesn't work, Yeah. No, the G1, essentially the X2, is basically an input they call virtual input. X2. That's a state, but is being treated as a virtual input for the first subsystem. So when I showed you the engine control, remember that problem that I showed you, the engine control? So I'm going to swap the slide. So look at that engine control. Let me So if you remember, we did that engine control problem that I showed you, the dynamics, simplified dynamics. See these equations. Now, you see these two equations. This is a strict feedback form. So the first subsystem is the total air. Now look at that, X2. What is X2? X2 is basically the total fuel. So you can view this X2 as a input to the subsystem 1. And here it's the second equation. The input to the second equation is the total, the change in the fuel, and basically the second input. So in this case, there's a difference between the first subsystem and the second subsystem. Here we are using the strict feedback form. Yeah. So there is a meaning to it, where each class, this is called a class of nonlinear systems. So I encourage you, those who took nonlinear control, go back to your Khalil book and see, it says strict feedback form. It should say that. Okay? All right, we're going to take a break. Right? We'll have tea and then we'll go look at pretty much the last part of the book lecture. And then tomorrow I'll play some videos. So this engine is a strict feedback system, not a fin system. Oh yeah.